Hey everyone! Ever wanted to build a neural network that can not only reconstruct images, but also generate entirely new ones? In this video, we're going to build a variational autoencoder, or VAE, a powerful generative model, using PyTorch and the MNIST dataset. We'll go through it cell by cell on Google Colab, visualizing results and generating digits from a learned latent space. Let's get started. What is a variational autoencoder? We are going to know about variational autoencoder by referring the architecture. Variational autoencoder, just like autoencoders, are a type of neural network designed to learn efficient data representations, primarily for the purpose of dimensionality reduction or feature learning. But variational autoencoders, VAEs, extend the capabilities of the traditional autoencoder framework by incorporating probabilistic elements into the encoding process. The goal is not just to compress data, but to create new data samples that resemble the original dataset. Variational autoencoders consist of two main parts. The encoder compresses the input data into a lower dimensional latent space. The decoder reconstructs the original data from this compressed representation. Let's start with the encoder. The encoder takes an image from the MNIST digit dataset as input. Each image is 28 times 28 pixels. This image is passed through a neural network, which compresses it into a lower dimensional latent representation. Instead of outputting a single vector, the encoder produces two vectors, one for the mean, mu, and one for the log variance, log sigma superscript 2. These define a probability distribution over the latent space. Using Bayesian inference, we update this latent space, posterior distribution, by combining prior knowledge with observed data. This allows the VAE to learn a meaningful and structured representation of the data. This setup allows VAEs to sample from the distribution, making it possible to generate new data during decoding. The latent space is a lower dimensional, continuous space where the input data is encoded. However, sampling directly from this distribution would break the flow of gradients during training. To solve this, VAEs use a technique called the reparameterization trick. Rather than sampling Z directly, we introduce a random variable epsilon, sampled from a standard normal distribution, mean 0, variance 1. Then, we compute the latent variable as Z equals mu plus sigma asterisk epsilon. In simpler terms, this formula generates a value of Z by starting at the mean, mu, and adding some randomness based on the standard deviation, sigma, and epsilon. This sampled point Z represents a location in the 2D latent space, a compact, abstract version of the input. Another neural network, called the decoder, is used to reconstruct the original data from the latent space representation. It takes a sample Z from the latent space and tries to generate an output that closely matches the original input. In other words, the decoder receives the compressed information and attempts to rebuild the image. This process enables the VAE not only to reconstruct input data, but also to generate entirely new data by sampling different points from the learned latent space distribution. The sampled latent variable Z is passed through the decoder to produce the reconstructed output X, which should be as similar as possible to the original input X. To train the VAE effectively, we use a loss function with two parts, reconstruction loss and KL divergence. The reconstruction loss measures how accurately the model can reconstruct the input data. The KL divergence, on the other hand, measures how different the learned distribution of the latent variables is from a standard normal distribution. This acts as a form of regularization, a technique used in machine learning to prevent overfitting and help the model generalize well to new, unseen data. In VAEs, regularization via KL divergence ensures that the encoder doesn't just memorize the training data. Instead, it encourages the model to learn a smooth and continuous latent space that captures the essential structure of the data. KL divergence pushes the learned distribution closer to a known, simple shape, standard normal, which helps the VAE generate high-quality, coherent, and diverse new data just by sampling from this structured latent space. So this is all about the architecture of variational autoencoder. Now, Head over to colab.research.google.com and open a new notebook. Make sure you're signed in with your Google account. And once you're in, let's write some code. We are going to upload the notebook since we have already written it. We start by importing the essential libraries: PyTorch for building the model, TorchVision for MNIST, Matplotlib for plotting, and utilities to help with data loading and visualization. Next, we load the MNIST dataset. Each image is transformed into a tensor and batched using PyTorch's data loader. We're using a batch size of 100 for faster training. The device is automatically set to GPU if available, otherwise, it defaults to CPU. Before diving into the model, let's visualize a batch of 25 MNIST digits. This gives us a quick look at what the model will be learning. Now we will start with VAE class. In this section, we begin by defining a VAE class, which inherits from PyTorch's NN module. This allows us to leverage all the built-in functionalities that make building and training neural networks in PyTorch much easier. Inside the constructor of the VAE class, we define three key components: the encoder, the probabilistic elements, and the decoder. The encoder takes the input data and compresses it into a lower dimensional latent space by passing it through linear layers with leaky ReLU activations. This transformation reduces the high-dimensional input into a more compact representation. Next, we send the output of the encoder into the layers that contain two parts: one for predicting the mean of the latent distribution, and another for predicting the log variance. This is where VAEs introduce their probabilistic twist. Instead of mapping the input to a fixed vector, the encoder outputs a distribution, typically modeled as a multivariate Gaussian. We'll later sample from this distribution during decoding, allowing us to generate brand new data points. The decoder, on the other hand, works in the reverse direction. It starts with a small latent vector and attempts to reconstruct the original input. The decoder ends with a sigmoid activation function because we assume the input data is normalized to be between 0 and 1. The encode function passes the input data through the encoder and produces the mean and log variance, which define the latent space distribution. In the reparameterization step, we introduce random noise, epsilon, and use the mean and variance to create our latent vector z. This trick, called the reparameterization trick, allows us to perform backpropagation through the sampling process, enabling proper gradient flow during training. The decode function takes the latent vector z and reconstructs the original input by passing it through the decoder network. Finally, the forward method ties everything together. It encodes the input data, samples z from the latent space, decodes z back to the original input space, and then returns both the reconstructed output and the parameters, mean and variance, of the distribution. Then, we instantiate the model and use the Atom optimizer to update weights during training. Let's now talk about the loss function, which is the key to how the VAE learns. The loss function takes four inputs: the original input x, the reconstructed output x_hat, and the two parameters of the latent distribution, mean and log_var. First, we calculate the reconstruction loss using binary cross-entropy. This measures how closely the reconstructed output x_hat matches the original input x. We use reduction equals sum to sum over all the pixels, which means if the reconstruction is bad, the loss will be bigger. Next, we compute the KL divergence. This measures how different the learned latent distribution is from a standard normal distribution. We want the latent space to be smooth and well-organized, not chaotic. Although the formula for KL divergence looks a bit complicated, the basic idea is this: mean POW2 penalizes large shifts from 0, log_var.exp adjusts for the spread of the distribution, and 1 plus log_var helps balance everything out. multiplying the result by -0.5 and summing it gives us the total KL penalty. Finally, we combine the reconstruction loss and the KL divergence. The model needs to both rebuild the input accurately and keep the latent space smooth and organized. And that's our VAE loss in a nutshell. It's a perfect balance between reconstructing the input and regularizing the latent space. Stick around. Next, we'll dive into training this model. Now let's talk about the training function, which takes care of training the VE model. First, we call model.train. This tells PyTorch that we're in training mode, so certain layers like dropout or batch normalization will behave differently during training. Next, we loop over the number of epochs. Each epoch represents one full pass through the training data. Inside this loop, we track the overall loss to monitor the model's progress. Inside each epoch, we loop through the batches from our train_loader. You might notice we ignore the labels with underscore because autoencoders, like VAEs, don't actually need labels, they're unsupervised models. We also reshape the input x into a flat vector, since the model expects a 1D input, not the original image format. And we move the data to the right device, for example, the GPU if available. Before making predictions, we always zero out the gradients to prevent PyTorch from accumulating them across different iterations. Then, we pass the reshaped x through the model to get the reconstructed output, the mean, and the log variance. We calculate the loss using our custom loss function that combines reconstruction and KL divergence. We add the current loss to overall_loss, so we can track how the model is performing across the entire epoch. Next, we back-propagate the loss with lost backward and update the model weights using optimizer step. At the end of each epoch, we print the average loss so we can see if the model is improving. Finally, the function returns the total loss, which you can use to visualize how the training is progressing. And that's the full training loop for the Variational Autoencoder. It's simple, effective, and sets us up to generate amazing results. Next up, this loop trains our model over 50 epochs. Each input image is flattened, passed through the model, and then we back-propagate the total loss. Notice how the average loss steadily decreases as the model learns to reconstruct digits more accurately. After training, we can sample any point in the 2D latent space and decode it into an image. This lets us explore how the model interprets different parts of the latent space. Each coordinate maps to a different style of digit, which is super interesting to observe. You can clearly see smooth transitions from one digit to another as you move across the grid. That's the beauty of a continuous latent space. Now, let's zoom out a bit and try with scale equals 5.0. You'll notice the digits become less realistic at the edges. This shows the model learned that meaningful digits tend to lie near the center. And that's it. You've built and trained a variational autoencoder from scratch in PyTorch, visualized its learning, and even generated brand new digits. If you enjoyed this walkthrough, hit that like button and subscribe for more deep learning content. Let me know in the comments what you'd like to build next.